Hey everyone, welcome. You gotta hear this because something huge just happened in the world of physics. We're talking about a brand new Nobel Prize that's not just another award. No, this one is basically opening a door to a whole new reality.
Yep, you heard that right. The 2025 Nobel Prize in Physics is here. And what it's for is, well, it's pretty mind-bending. It's for something so fundamental that it connects that super weird world of tiny atoms with the world that you and I live in, the one we can see and touch. And look, this isn't just some trophy for a few scientists. This is a launchpad for the next big tech revolution.
Okay, so here's the plan for our explainer today. We'll start with the Nobel Prize itself. Then we'll get into the science, but don't worry, we'll keep it simple. We'll see how this tech goes from the lab into your life, meet the brilliant minds behind it, and look at what's next. And you know what? We'll also explore India's amazing connection to all this. Ready? Let's dive in.
All right, first up, a Nobel for quantum leaps. Let's talk about what just happened and the people who made it happen. The big announcement sends a really clear signal. The quantum age, it's officially here.
So here's the scoop. The prize is going to 3 scientists based in the US, John Clarke, Michel Devoret, and John Martinis. And what did they do? They basically proved that these totally bizarre quantum effects, like particles just walking through walls, can happen in an electrical circuit that we can build. But the real kicker? It's the timing. This is the second Nobel for quantum mechanics in just 3 years. That's huge. It tells you this stuff is jumping out of the textbooks and into the real world fast.
Okay, let's get into the science. And I know macroscopic quantum tunneling sounds like something straight out of a Marvel movie, right? But trust me, the main idea behind it is actually pretty easy to get your head around. Let's break it down.
So first up, macroscopic quantum tunneling. Now forget thinking about just one tiny little atom. We're talking about a whole system here, a massive group of particles inside an electric circuit, all acting together like a single team. And quantum tunneling? Well, it's that wild ability a particle has to just pass right through a solid barrier, like a ghost. What this discovery proved is that it's not just one tiny electron that can pull off this trick. A whole bunch of them, working together in a circuit we can actually build, can do this magic.
This is the best way to picture it. Okay, in our normal everyday world, imagine a ball stuck in a valley. To get it to the other side of the hill, you have to give it enough of a push to roll all the way up and over, right? Simple physics. But in the quantum world, things get weird. The quantum ball doesn't need to roll over the hill at all. It can just poof, instantly appear on the other side. It literally tunnels right through without ever having the energy to make the climb. It sounds impossible, but that's exactly what these scientists proved can happen on a big scale.
Okay, the second big concept is energy quantization. And the funda here is actually really simple. See, in our world, energy feels continuous, kind of like water flowing from a tap. But in the quantum world, nope. Energy only comes in fixed, discrete packets called quanta. So you can have 1 packet of energy or 2 packets, but you can't have 1.5. It's just like money. You have a 10 rupee note, a 20 rupee note, but there's no such thing as a 15 rupee note, right? It's exactly like that. A staircase with clear steps, not a smooth, continuous ramp.
So why is this so important when it happens in an electric circuit? Well, because by proving that energy has these fixed levels, they basically created a giant, man-made, artificial atom. Just like a real atom, their circuit had these predictable, stable energy steps. And that right there, is the absolute core principle of a qubit, the basic building block of a quantum computer. You literally cannot build a quantum computer without this.
All right, enough of the heavy science for a minute. We've got the basic ideas down, but the real question is, so what? Why should you care? How does some weird circuit in a lab change your life? Well, turns out it changes pretty much everything.
You see, this discovery was the missing link. Step 1, it proved that quantum rules aren't just for tiny invisible things. They work for bigger systems we can actually build and control. Step 2, with that proof in hand, we got the blueprint and the confidence to start building real quantum tech, which leads right to step 3, a total revolution in computing. I mean, the powerful superconducting qubits that companies like Google are building today, they're the direct result of this Nobel-winning work. And it doesn't even stop there. Step 4 is about creating super-sensitive sensors. Just imagine a device that could map your brain activity in real time, no surgery needed, or find valuable minerals buried deep in the earth. That's the kind of power we're talking about.
Cello, let's rewind a bit and look at the history here. Because a breakthrough this massive doesn't just happen overnight. It's built on the work of giants, over decades of really hard work by some absolutely brilliant minds. Just look at this journey. It really starts 100 years ago, back in the 1920s, with the theoretical groundwork laid by geniuses like our very own S.N. Bose and, of course, Albert Einstein. Then you fast forward to the 80s, and you have some early experiments that hinted something was there. And then bam, 1984-85. That's when our three winners did their crucial experiments. And you can just see how things are speeding up now. The Nobel in 2022 was for quantum entanglement. And now, just 3 years later, this one. We are truly living in a golden age for quantum science.
So let's put some faces to the names. First, you've got John Clarke at UC Berkeley. The guy's a pioneer in using these incredible devices called squids. They're basically the most sensitive magnetic detectors on the planet. He used them to show that these tiny quantum effects could actually be measured.
Then there's Michel Devoret, who actually worked in Clarke's lab. Today he's at Yale. But get this, he's also a key scientist at Google's Quantum AI Lab. That's a direct line from 80s research to today's quantum computers.
And rounding out the trio is John Martinis. He also worked with Clarke and Devoret, and he later went on to lead the hardware team at Google, building some of the most advanced quantum chips we've ever seen. So you see, these guys aren't just theorists. They are the people who literally built the quantum age.
Okay, so the proof is there. Does that mean we're all getting quantum laptops next year? Not so fast. The road from here to there has some really, really big hurdles to overcome.
Yeah, there are a few major challenges. First up, temperature. These quantum circuits have to be kept incredibly cold. We're talking colder than outer space. That's a huge engineering challenge. Next is something called decoherence. The easiest way to think about it is like this. A quantum state is super fragile, like a soap bubble. Any little vibration or noise from the outside world and poof, it's gone. The whole calculation is ruined. Then there's scaling. Right now we can build a few hundred qubits, but to do anything really useful, we need millions. That's a giant leap. And finally, error correction. Because these systems are so fragile, they make mistakes. A lot. So we need to figure out clever ways to catch and fix those errors on the fly.
And now, for a part of the story that's really fascinating, and one that makes me quite proud, India's connection to this whole quantum revolution. And it's not a new thing. Our role goes right back to the very foundations.
It all comes down to this. 100 years ago, the brilliant Indian physicist Satyendra Nath Bose came up with the mathematics to explain how a group of particles could act together like one big quantum wave. His work, which we now call Bose-Einstein statistics, is the theoretical foundation for all of these large-scale quantum phenomena, including what this Nobel Prize was awarded for. His work was just light years ahead of its time.
And this table here is a great way to see the big picture. You see, this Nobel-winning discovery is part of a larger family of macroscopic quantum effects. You've got Bose-Einstein condensates, which are used for super precise measurements. You've got superconductivity, which is in MRI machines. And now you have this quantum tunneling in circuits, which is the key to quantum computing. They are all different sides of the same amazing idea. Quantum mechanics working on a scale we can see and use.
And that brings us right to the present day. India is not just looking back at its history. We are actively building the future with the National Quantum Mission. We're talking about a 6,000 crore rupee investment to make India a world leader in this tech. Our best institutes, TFR, IISc, the IITs, they're all working on this, building our quantum future. The legacy of S.N. Bose is truly alive and kicking.
So I want to leave you with this one big thought. For 100 years, quantum mechanics was something we just observed, a weird property of nature. But now, we're not just observing it, we are engineering it. We are building devices that are designed from the ground up to follow these strange and powerful rules. So it really makes you think, if we can teach a circuit to obey quantum laws, what's the limit? Are we on the verge of engineering reality itself?
And that wraps up our deep dive on this incredible Nobel Prize. Look, I know some of these ideas are pretty mind-bending, so to really get a grip on it, do check out our website. We've put together some fantastic detailed notes and a really useful quick revision mind map. The link is right there for you in the description below. Thanks so much for joining me on this.